Hi guys, welcome back to Introduction to Mechanical and Automotive Engineering. I'm your lecturer, Dr. Elizabeth Kiriakou, and we are still solving questions that are similar to our mid-semester exam. And in this question, it actually asks us to determine the force in the pin A, B and C. Okay, so we know that we're going to have X and Y components for each of these. So how do I solve this? I have quite a few unknowns, so if I take a section through this pin, I'm going to end up having member AC, and I'll also have member CB. So I'm going to split this up into two separate problems. So let's take a look here at member AC and member BC. So in this one here we have A and C, and over here we have B and C. So when we break the frame into two parts, we need to make sure that everything stays in equilibrium, and these forces are going to be equal and opposite. So here I'm going to have a CX, which means on this side I'm going to have equal and opposite, another CX, and here I'll have a CY, and on the other side I'll also have a CY. Okay, so now what do we need to find? We also have reaction forces at A. So at A I have an AX and an AY, and over at B I have a BY and a BX. Okay, let's put on our other forces. So here we have 800 newtons, and we need to convert this distributed load into a concentrated force. So it's going to be perpendicular, and it's going to sit halfway along this member. So we need to actually calculate what this concentrated force is, and to do that we actually need to get some geometry. So if I just look over here, I have, this is my height of 2 meters. If that's 60, then this length is going to be opposite on adjacent. So it's going to be cos 2 on sine 60, actually. So now we can actually calculate what that force is going to be. So if that's in meters, here I have the member, and it's going to be 200 Newton on the meter times by 2 on sine 60 meters. The meters will cancel out and I'm left with newtons. So it's going to be 400 on sine 60, and that sits halfway through. So that's 400 sine divided by sine 60, and this distance here, if the whole length is 2 sine 60, that means that's going to be 1 on sine 60. You can actually calculate that out if you like. So now that we know what this load is, so here we have 400 on sine 60, and we have our perpendicular distance, and that is 1 on sine 60. So I can now break this up into its horizontal and vertical components, and once I've done that, I can actually find some of the moments around A and I'll have an expression for Cx and Cy. And then I'll do exactly the same thing in member BC. I'll be able to take some of the moments around B and find an expression for Cx and Cy, and then solve the two questions simultaneously. And for our equations for equilibrium, some of the forces in the x direction equals 0, some of the forces in the y direction equals 0, and some of the moments around a point has to equal 0. So let's take a look. We've got some geometry going on. That's 2 meters, that's 60 degrees. So this distance here is going to be 2 on tan 60 degrees, meters. And I can actually break this force up into its x and y components. So this angle here is also 60 degrees. So I can say I take some of the moments around A, some of the moments around A has to equal 0, and I'm going to have Cy is going in this direction, so it's positive. So Cy 2 on tan 60, that's my perpendicular distance. I'm also going to have Cx, and that's going positive. For Cx, my perpendicular distance to A is 2 meters. And then I'm going to have the x component of this force, or I can just calculate. I already know what my perpendicular distance is, so I actually don't really need to break it up into its x and y components. Okay, so I'm going to have minus 400 on sine 60, and the perpendicular distance is 1 on sine 60, because we already calculated that perpendicular distance. So this will be equation 1. If I now take a look at this member, I can take some of the moments around B, and again to find an expression for Cx and Cy. So let's say some of the moments around B has to equal 0. And what do I have? I have this 800 kilonewton, and my perpendicular distance is 2 meters. And we also need a distance along here, and that's also 2 meters. So Cy is going to go in the positive direction. So I'm going to have Cy, my perpendicular distance is 2. I'm going to have Cx, that's going negative, and my perpendicular distance also is 2. And then I'm going to have the 800, and that's going positive, so we plus 800, and my perpendicular distance is 2. So if I calculate that out, I can call that equation 2. So again, I have 2 unknowns in each equation, and I can solve equation 1 and 2 simultaneously, and I should have a value for Cx and Cy. So I've already calculated this, and Cx is going to equal 416.8 newtons, and Cy is going to equal minus 338.1 newtons. Okay, so now I can put these two numbers back into these two free body diagrams, and I should be able to do some of the forces in the x direction will give me Ax, some of the forces in the y direction will give me Ay, and similarly on this side, when I substitute the numbers in, I'm going to be able to find some of the forces in the x and the y direction to give me Bx and By respectively. So let's take a look. So I'm just going to clean this up, don't forget those numbers. I'm just going to write them over here. have Cx equals 461.8 newtons, and Cy equals minus 338.1 newtons. So we'll just remember that. So that's also what the question asked me, and it asked me what the reaction forces were at pin C. So there's one of my answers. So if we look at this member here, if I say sum of the forces in the x direction has to equal 0, what do I have in the x direction? I have ax, and let's just put an axis in here. I should have written it before, x and y. And I'm going to have this force in the x direction, so that's going to be plus 200, actually I called it 400 on sine 60. And my x component is going to be sine 60. And I'm also going to have minus Cx, I've already calculated Cx. So Ax is going to equal 61.88 newtons. So that's my x component at A. Now if I take some of the forces in the y direction, what am I going to find? Ay. So I can say sum of the forces in the y direction has to equal 0. What do I have in the y direction? I have a positive Ay, I have a positive Cy, and I have the y component of, and that's going negative, of my concentrated force. And that's going to be cos 60. Remember that this is a negative number, yeah? So we need to put the whole negative number into that equation. So then Ay is going to equal 569 newtons. So now I have my reaction forces at Ax and Ay. We're going to do the same thing for this member, and we can find the reaction forces at Bx and By. So it's pretty straightforward once you know how to actually break the problem up into two components. Okay, so now let's take a look at this one. So we have sum of the forces in the x direction has to equal 0, and what do we have in the x direction? We have Bx minus 800 plus Cx. You know what Cx is, so Bx is going to equal 338.1 newtons. And then we can say that sum of the forces in the y direction has to equal 0. We have minus By minus Cy. And remember, Cy is already minus, so we're going to have By minus 338.1 newtons. So By is going to equal 338.1 newtons. So there we have it. We've found our forces, our reaction forces at A, B, and at C. If we wanted to take the internal loads and find the internal loads at any point now, that's actually quite simple. If we want to find the internal loads across here, what do we need to do? We can actually just look at this part of the problem, okay? And we should be able to find what the internal loads is at this point, okay? So simply, it's going to look like, so here is B. I've taken my cut here. So here at B, I have a x and a y component, so which I've calculated, Bybx. And I'm going to have a normal force, a shear force, and a moment. And you should be able to calculate that. So I think the most difficult part in these problems is actually knowing where to cut the section, and knowing and being aware that you may have to solve a simultaneous equation.